This is the second part of the N-gram language models presentation. As usual, when we have a model, we need to know how good our model is. So now we're going to talk about evaluation, how to evaluate a model. And as usual, as in machine learning, we always have one training set and the other is the test set. So let's see what is in the training set. So in the training set, we have sentences. And then we use those sentences to build the n-gram language model. If you pick the n equals 2, means you're using bigram model. You may use the other values of n as well. Now you have another set of sentences. We call it test set. And then again, as usual, these sentences, you're not supposed to look at these sentences in the test set. So you just take away some sentences from your corpus and put it aside in the test set. Now, what to do in the test set? Use the probabilities that we obtained from the training set. So you have trained an n-gram model. You have obtained all the probabilities. Now you use those probabilities to compute the joint probability of the sentences in this test set. Means that you are going to measure how likely these sentences are. Of course, the higher is the better, because how to say it? These sentences are actual sentences, sentences that really exist. So of course, their probability must be high because they are actual sentences. So if you're comparing two n-gram models, the better models should give the higher joint probability for the sentences in the test set. Again, if you're comparing two models, the better model should give the higher joint probability for the sentences in the test set. Now, somehow the measure is not directly on the joint probability itself, but on the inverse. So 1 over the joint probability. And that metric is called perplexity. Because we would like to have the higher joint probability, if we take the inverse, means that the lower perplexity is the better. We have two equations here. The first equation is we are computing the joint probability without any approximation. So remember that without any approximation, the history means that the history contains the sequence from word 1 up to word I minus 1. But then when we want to do some approximation, let's say using bigram approximation, then correspondingly, the way to compute the joint probability is that if you compute the probability of word I, you only need to care about the word at position I minus 1. So that's the only difference. The second formula for perplexity is based on the bigram approximation. But the idea is still the same. Perplexity is 1 over joint probability. And then the lower perplexity is the better. Now, there's one problem with dividing the data into training and test set. Sometimes there are words that we never see in the training set occur in the test set. Suppose a very rare word like aardvark or something, somehow it never appears on the train set, but it appears on the test set. So how can we handle that? We are going to do some smoothing, and I'm going to introduce just one method of smoothing here. It's called Laplace or at-once smoothing. Of course, there are other ways to do this, but I'm introducing the idea. What is exactly the problem with the word that we see in the test set, but we've never seen it before in the train set? Well, if you think about it, you want to compute the joint probability of the sentences in the test set. However, if there's a word in the test set, let's say aardvark, you've never seen it before. So the probability of, let's say, aardvark given I or given want, then it should be 0. Then the entire sentence will be 0 because The join probability is you keep on multiplying the probability of this times probability of that times probability of the next word given the previous word and so on. So if any of those elements is 0, now the entire join probability of your test set becomes 0. So it's really not a good metric or measurement if everything just falls to 0. So this is one idea to avoid that kind of thing. So this is the original counts, the table that we've seen before. So I followed by the word ones is 827 times. As the name suggests, add one smoothing is very simple. You just add 1 for each of this bigram pair. So here you see the number 5, now it becomes 6. I followed by 2, previously it was 0, now it becomes 1. So every number that you see in the original counts, you just add those numbers by 1. So anything that was 0 previously now becomes 1. Is this the best way to do smoothing? Well, maybe not, but this is kind of an idea to introduce you to the smoothing. Now let's see how smoothing changed the bigram probability. Without smoothing in the denominator, you count how many times the previous word or the word n-1 appears. And then in the upper part of the equation, you count how many times the word n-1 followed by the word at position n. How many times those two words appear together. Now with smoothing, we add every appearance of word n-1 with word n. We add 1, and also with every word that follows the word n-1, we also adding it by 1. And then it may be simplified to look like this. In the upper part, it is added by 1. And then in the denominator or in the lower part, we add it with the number of words in our vocabulary. So this big V is how many words you have in the vocabulary. Finally, let's see how we can use an n-gram language models to generate some text. This is pretty interesting actually. So first, let's see the result of sentences that are generated by unigram model, bigram model, trigram model, and quadrigram model. Unigram model means just each time you just pick one word based on the probability of that word. So the more frequent a word appears, it has a higher probability. And then bigram means that you start picking the word Y as the first word following the start, and then those is the second word following Y, and then so on. So this is the bigram model. Trigram model, you will pick a word based on the history of the two words before it. And quadrigram means that you are picking the fourth word based on 3 words that appear before that. Now notice you might not be very familiar with Shakespeare's books, but you can see that when you increase the value of n, the sentences look more and more reasonable. This is another sentences that are randomly generated using the corpus from Wall Street Journal. Again, you can see that the sentences from unigram does not really making any sense. Like months, the my, and issue is just weird. Using bigram, it is quite okay. Looks like a sentence enough. Last December threw away to preserve the Hudson Corporation. It's pretty good. Trigram looks even better. They also point to $99.6 billion from 204.63%. It doesn't make any sense, but it sounds like an English sentence. On the practical side, how can we generate such text? I'm going to show you an example to create the text using bigram model. So first you start with the symbol of the start of the sentence. And then let's say this is your bigram model. You only have two possible words that follows the start symbol. The probability that I is the first word is 0.23. The probability of the word U is the first word is 0.77. Now you may draw something like this. On the range from 0 to 0.23, it belongs to the word I. On the range from 0.23 to 1, it belongs to the word U. Now you throw a random number. Let's say you get 0.89. It falls here. So you know that you're picking the word U as the first word. So now your sentence is start symbol followed by U. Next, you see what are the words that are likely to follow U in your n-gram model. Suppose again only two possibilities here, so either like or dislike. Again, let's say the probability of like following U is 0.55. The probability of dislike following U is 0.45. I just made up this number for this example, so don't worry about how to get these numbers, okay? Again, you throw a random number. Let's say you get 0.13. So here you will get this word like. So now your sentence is you like. Keep going to see if the history is the word like. What are the possible words that follow it? Suppose again only two words that are possible, mango or lemon, with this probability. And then you throw a random number again, and then you get mango. So now the sentence becomes you like mango. And then somehow the word mango can be followed by the end of the sentence with a pretty high probability. Then we throw a random number, 0.25, and then hey, we get this end of sentence symbol, so now the sentence is complete. If not, you just keep going until you get this end of sentence. So that's how you generate a text. Of course, the sentence that you generate may not making any sense like this, because this is just an example that I made up. So the sentence makes sense, but otherwise it may not make sense. But it's something interesting to try. And then also on the practice side, this n-gram language model is not very difficult, I think, because mostly you only use counting, counts how many times this appears, how many times this and that word appear together, then just divide this by that and so on. So only counting and keep the frequency. Let's say you use a dictionary in Python or something. So that's the end of the presentation for this n-gram language model. I hope you find it useful. And then as usual, if you have any question, feel free to leave your question in the comment, send me an email or a message through IDE. Or I set up a forum of Q&A in the IDE. Please check out that forum. Thank you.